Righty ho. So, I'll get straight into it then, if I can. Right. So, as just starting off, the whole thing about this topic is you when you get into it, you are up against the world, and the world is basically saying you're wrong, but you have to have kind of have to have a bit of courage to stand up against people, and stand in your conviction because this is what it's like. You're standing up against the crowd saying, "Yeah, all of you, you're all wrong." But where I am at the moment, that's exactly how I feel. I don't care if everybody thinks I'm wrong. I've actually seen all this for myself, so I know, deep in my heart that I'm on the right track here. So the thing about this is that we're looking at two polar opposites, sort of two arguments here, globe Earth and flat Earth. But on the surface, they look exactly the same, right? Just like this image, right? You can't tell whether the train's coming out of the tunnel or going into it. Okay, there's not enough information. There's three frames of information being repeated. You can't tell which is which. You have to look at something external so that you can figure out which way it is. So just like if you're on a train and there's a train next to you and one of the trains starts moving, initially you can't tell which one's moving, right? Unless you look at something external like a post, right? You can tell which is moving. So this is exactly what the flat Earth's like. It's two polar opposites, but they look identical, right? One of the things you have to also be aware of, and I'll stop this for a second, is how easy it is to be fooled, especially by two-dimensional media. Yeah. So photographs and video, you have to pay close attention. So let me play this. All right. So we went into looking at that video with a certain mindset because we all know what a room looks like. Yeah. And it blinded us to certain things that would have given the game away, like the difference in color in the cups. And there's a black rectangle underneath the chair and the strange angles of the picture on the wall. Right. We kind of ignored that and we saw what we wanted to see until each one of those was kind of dispelled, right? So again, we can't trust two-dimensional media, and especially now with AI, literally anything can be produced for us. So this is a story we're told. We live on a spherical Earth, and it's rotating at 1,000 miles an hour on a 23.4 degree tilt. And we're orbiting a star 93 million miles away at 18.5 miles per second. I'm saying it in those terms because when I was searching, that's what I found. And we're moving at, the sun's moving at 480,000 miles an hour, and the galaxy itself is moving at 1.3 million miles per hour. Yeah, and it's all supposedly held together by gravity. Here's the thing. When you start looking into all the figures associated with this model, you keep seeing a certain number, and anybody who's been looking at truth over the last few years will recognize this number as a calling card of a kind of Luciferian brotherhood that have taken over this world essentially. So when you look at what the curvature of the Earth over 10 miles is, you'll find it's 66.6 feet. Yeah. The Earth is tilted at 23.4. I always thought it was 23 and a half, but when I looked further into it, it was actually 23.4. But that's 66.6 degrees away from the horizontal. Yeah. 18.5 miles per second works out at 66,600 miles an hour. They usually round it up to 67,000 miles an hour. But this is why I found 18.5 miles per second. When Newton discovered gravity, it was in 1666. Yeah, and the force of gravity is 666 newtons. And as I said, there's so much more. Everywhere you look about this model, you'll find that this number keeps coming up. And yeah, it's, as I said, it's a calling card for the people who are the architects of this model. So how do we know what the shape of the Earth is? Well, our senses literally tell us we live on a flat, non-rotating Earth. That's it. It's what our senses tell us, right? So, you can go down to the beach. What you see is a flat horizon. Yeah, you don't feel any motion, and we've got very, very sensitive senses, especially for acceleration. But we don't feel any motion whatsoever, and our intuition tells us, there is only one direction for down. It is kind of counterintuitive to know that down is, according to this model, down is also that way and that way and that way and all sorts of other directions. But our intuition tells us down is only one direction. And none of us have been to space. As we're just being told via two-dimensional media that there is space and there are people up there, right? And there's no way you can prove any of this model. I think it was even Einstein who said there is no test that can show the motion of the Earth, right? There is no way of proving any of this that we've been told. So how we believe or come to believe this is that we were taught, right, from the very earliest times of our lives, when we were unable to analyze information as it came into us. We were told, here's a globe, this is where you live on this globe. And, our minds at that time couldn't really question it. It was okay, because before the age of 6 or 7, everything you learn becomes the absolute truth. Your absolute bedrock of your reality. And this is why, basically one of the very first things they do is get that globe out, right? Funnily enough, when you look at the bottom of those globes, it actually says globes are not meant for educational purposes, but only for decorative purposes. So it kind of tells you, lets you in on the secret there. So after school, right, you just get relentless programming. Everywhere you look, you see the globe. You see it reinforcing this idea you live on this globe, right? And it doesn't stop. So this is a choice. We know what we experience every time we look, but they're trying to make us believe that we live on this spinning water ball, right? This which really, if you step back, doesn't make any sense whatsoever. Now, this is just my view. Everyone's free to have their own view, but to me, the picture on the left makes more sense to me. So this is a model that the mainstream says that we believe in, that we're on, us flat earthers think we're on this pancake floating in space, and there's an edge that we can fall off of, right? On the contrary, what we actually believe is more like a lake. If you imagine a large circular lake, right, with the shoreline, the bank of the lake being the edge, and there's islands in that lake, which are the continents. So just as you see the edge of a lake there, the edge of our world is what they call the Antarctic shelf, which is the highest continent on Earth, right? Which when you approach it, I think it's a 200-foot wall of ice, right, that you have to scale, and then there's something like 300 miles of Arctic desert or Antarctic desert, which gets colder and colder and colder, and then beyond that, very very few people know what's beyond that. In fact, Captain Cook, 1773, he actually sailed around Antarctica to try and find an inlet. Um, um, and he ended up sailing for 60,000 miles over 3 years. Right now, the circumference at the equator is 24,901 miles. So how can he sail all the way around Antarctica and sail, almost three times the distance of the circumference, right? If it's a flat lake, then that's easy because obviously the edge of the lake is a lot further round than the center ring of that lake. But on a ball, impossible. And the idea that we are in an enclosed system with a firmament above us, where the stars are kept. Well, it can't. It's not that extraordinary. Since if you've ever gone to a planetarium, I mean, I remember going to a planetarium in the States, and it was a huge thing. And when they projected the stars up there, um, they seem to sort of have winds in there, and they made it sound like you were outside, and it felt like you were outside, and in the world, but literally you were in an enclosed system with stars being projected over you. Um, so it's not that much of a stretch, really. So I'm actually in this presentation just going to talk about three different aspects of the flat Earth because there's so much I could talk about. I'll just have to limit it. So I'm going to be talking about the curvature, and part two will be the motion of the Earth, and I think part three I can't remember because I cut out a lot of stuff. Part three will be about space. So part one, curvature. Because the Earth is 24,901 miles around, right? The curvature has a very particular amount of curvature. It's 8 inches per mile squared, roughly. That only really works for a quarter of the Earth, but for our purposes, it's a very good rule of thumb. But the point is that the Earth should have a physical barrier, right? So the further you look, the more this physical barrier will obscure what you're looking at. So this is how I got into it. So when I saw this experiment on YouTube, had nothing to do with flat Earth, but it told me this 8 inches per mile squared distance to calculate how much curvature should obscure a landmark. So I went down to Plymouth Hoe, and I knew that the Eddystone Lighthouse was, I thought it was 12 miles. It was about 13 and a half miles away from Plymouth Hoe. So I got my zoom camera, and I was about 30 feet, around about 30 feet up from the actual water, and I zoomed in on the lighthouse. Now, according to the Earth Curve calculator, I should have lost the first 32 feet of that lighthouse. So the first 32 feet of that lighthouse should have been obscured by the physical curve of the Earth. Okay. So I zoomed in on it, and I could see where the water met the rocks. Actually, in this picture, it's high tide, but when it's low tide, you can actually see the rocks that the plinth is standing on. I could see where the water was splashing up against the rocks, even though I should have missed the first 32 feet of that lighthouse. But more than that, I could see the horizon behind, right behind the lighthouse, where the horizon should have been. Well, it should have been 6 miles in front of the in front of the lighthouse. The horizon was way behind that lighthouse. So that's what launched me into this, because um, if if I couldn't detect curvature, there's only two explanations. Either the Earth is much, much, much bigger than they've told us that it is, or it's a flat Earth. So from there, I've been doing experiments all around the world to figure out which one it has to be. So just on the same sort of note, this picture was taken from Boulogne at the White Cliffs of Dover. And again, you aren't supposed to be able to see the White Cliffs of Dover from Boulogne, because I can't remember how it is. I think it's I can't see it anyway, but it's literally the top of the cliffs is below the mountain that should be hidden by curvature. Yeah, so you shouldn't be able to, but on good days you can see the White Cliffs of Dover from Boulogne, and likewise, there's been a couple of clear days. Now I live on the south coast near Brighton, and on a couple of clear days you can actually see France. Again, you're not supposed to be able to see it. We're also told that the size and shape of the Earth was proven to us 2,000 years ago by a guy called Eratosthenes, right, who did an experiment with two sticks. So in one place, I think it's Alexandria, he had a stick in the ground, and at a certain time, like midday in Alexandria, the stick in the ground cast no shadow, so the sun was directly overhead. But 400 miles away, exactly at the same time, a stick in the ground cast a shadow, and he was able to work out how much the Earth curved. But the problem there is that it assumes that the light coming in from the sun is parallel, as it should be if the sun is 93 million miles away. All the light received by Earth should be coming down parallel, kind of like this at the top. But that's not what we see, is it? We never see light coming down like that. We always see light coming down at angles, basically going towards where the light is. Yes, some of that, when it's directly in front of us, is actually perspective. But when the sun's in front of us, we can see light coming down at all angles. So it's not just perspective, right? So essentially, turns out if the sun was 3,000 miles away and 32 miles across on a flat Earth, you'd get exactly the same results as Eratosthenes got, right? So again, it's like that train I mentioned at the beginning, that they're identical, right? You've got an identical explanation for both, right? But it's just an external. You have to look at something external to be able to figure out which one's right. And the external thing here is light, the way the light is received on Earth. As we see, we see through experience, light does not come down parallel. It always comes down at angles. So it tells me that this is the truth, because otherwise, because Eratosthenes didn't take diverging light into account with his calculations, right? That means the Earth must have been way smaller, according to his calculations, right? Just put these things together. Another thing is that if the Earth, is a globe, and since the Earth is like 70% water, then the water must be curved as well. But here I'm showing you a picture of Lake Baikal. Now, Lake Baikal, it's in Siberia, and I think it's might get these numbers wrong, 163 miles long, right? And every winter it freezes over, right? And so when it freezes over, literally the whole lake is frozen over. But it is absolutely flat over that 163 miles. Now, there should be a hump in the water. If it was a globe, there should be a hump in the water. And I'm doing this from memory now. I think it should be something like 5 miles high. But literally, you can see the reflection in that frozen ice, and it's a flat reflection, because if there's any distortion in a mirror, you notice it, you see it, okay? But you cannot see that any distortion in that reflection. There's also a place in Bolivia called Salar de Uyuni, which is a salt flat essentially, and it's 80 miles long. Now, when it rains there, literally that whole salt flat is covered with about an inch of water, and it forms again a perfect mirror. No distortion whatsoever. It's such a perfect distortion, or a lack of distortion, that people who go there say it's like walking in the clouds, because you can't tell where the land and the air, land ends and the air begins. Yeah. So we see no evidence of curvature whatsoever. So there are people who say, "Oh, I've seen the curvature myself," right? Especially from an aircraft, right? So they say, "Well, I looked out the window and I could see curvature." Well, what they're not taking into account is the aircraft body is curved, so the windows are curved, and also there's an internal window which is pressurized as well. So that kind of ends up bulging outwards as well. So when you look at this picture taken from the window, you can see that the wing is curved when it shouldn't be curved like that as well. And sometimes you can actually see curvature from out the window while the plane's on the ground as well. So no, you don't see curvature from the plane. There was this Red Bull atmospheric jump from this guy called Felix Baumgartner a few years ago, and this was what was shown to the viewers. He was 128,000 feet up. I think that's nearly 24 miles. And yes, he said, "Oh, I can see the curvature." Okay, but below him is New Mexico, where he took off. So that's like we must live in planet New Mexico, because New Mexico has taken up most of the Earth there. Yeah. So it says, "Can you see curvature from 128,000 feet?" Right. This is from Neil deGrasse Tyson, who's commenting about this jump.
And that dude who jumped out of a perfectly good balloon, what's his name? Felix Baumgartner. He would have been about 2 millimeters above the surface of this globe. That's his edge of space jump. Now, I don't. It's fine. He wants to. I don't have a problem if he does it, but the honesty of it would greatly diminish what I think people thought he was actually doing. And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines. Right. So in the photo, you see this curvature of Earth's surface, and he said, "Wow, he's in space. Look at that." No, he's not. At that height, you don't see the curvature of the Earth if you are 2 millimeters above this beach ball. You just don't. That stuff is flat.
Nice admission from Neil deGrasse Tyson there. But you can see he's telling you that is a wide-angle lens making that curvature. There was no curvature. In fact, the internal camera, that when the door opened, you could see that the horizon was flat from that camera. This is the oldest proof that the Earth is a globe. Let me go back to it.
If you send a ship straight to the horizon, right, eventually it begins to disappear until it's no longer visible beyond your horizon.
Right.
And you should ask yourself, what kind of surface would produce that result?
So right there, on one hand, he says that you cannot detect any curvature from 24 miles up. Yet you can see a ship go over that curvature from standing on the ground. There's a little bit of a disconnect there. But, one of the problems there is that, if you're a 6 foot person, your horizon is 3 miles away. Okay. So somebody 6 foot, their horizon, so where that curvature sort of blocks your view, is 3 miles. So that ship is disappearing 3 miles away. Okay. But the point is, when you look to your left, you can see for 3 miles. If you look to your right, you can see for 3 miles. So somehow there's no curvature sort of left or right, but yes, there is a curvature right in front of you. So do we live on a cylinder? It doesn't make sense until, we got hold of this camera, the Nikon Coolpix. It was a P900, but there's a P1000 now, which is the flat earth camera of choice because it's got an amazing zoom on it. What we find, and here's a little experiment, piece of wood there, and it's perfectly flat. There's a boat on the end of it, and we can zoom in. And well, when we start, we can't see the boat because it's obscured by the flat board. But when we zoom in, it comes back just like it works in real life. Yeah. So let me just play that bit again. So we're just zooming along that board, and there's a boat at the end. And this is what it looks like from the camera. So don't know if you can see my pointer. We're going to zoom in on this plank here. And the boat comes into view. And as I said, it's exactly the same as we see down here in this picture, as we zoom into an empty horizon, and a boat comes back from over the curve. Yeah. So what we find is that, when a boat, we can actually see with our naked eye, a boat seemingly go over the curve, but then we whip out our zoom camera and zoom in, and the boat comes back. And we can stay at that level of zoom and watch the boat again go over the horizon, and then zoom in some more, and it comes back. And it keeps coming back to the limit of the zoom of our camera. So there is no curvature that we can detect. Funnily enough, Nikon suddenly decided, right, on February 29th last year, to discontinue selling these cameras, right? Because they were actually making a lot of money out of us because we were buying these cameras left, right, and center. Right? Turns out, same day, NASA signs an agreement with Nikon to develop their Artemis camera, which is a lucrative contract. So I can almost guarantee that that NASA said, "We'll give you this contract. You just have to stop selling these cameras." Right. So a common argument that comes back from people who say that when we point out that, look, we can see things that are way further than the curvature of the Earth, they say, "Oh, it's refraction, you idiot." Yeah, refraction. Well, the thing is about refraction is what refraction does is it inverts an image, or it squashes it, or it expands it, but it doesn't take something from behind an obstacle and bring it in front of it. Most people are familiar with refraction, like on a hot day when they look up the road and they see a car coming, and it looks like the car's coming at you through water, but there's no water. It's literally reflecting the bottom of the car and the sky, so it looks like it's water, but no, that's what refraction is.
As shown here and in countless examples, refraction is real. It compresses, it stretches, it distorts, it obscures and mirages. You can see it with your own eyes. But the globe propagandists have hijacked the term refraction and took this observable reality and deceptively changed refraction into an imaginary Earth curvature removing device.
So there is, you can see the refraction as the temperature and humidity goes up and down. Right? Literally, it just distorts the image. It doesn't bring things beyond the curve. So I was on the salt flats in Utah, Bonneville Salt Flats, and I took this picture, and it looks like land floating in the sky, doesn't it? But really, what's happening here is that there's a band of reflection. So the heated air is actually reflecting the sky, what's above it, and it's literally hiding the actual horizon. So the horizon is somewhere in that band of reflection. It's not the bottom of that reflection. That's a false horizon. The horizon is somewhere in that reflection. Right? So it's just literally inverting it. And I'm not going to play this all of this because it's a few minutes, but this is just watching a boat going out to sea, and as the boat goes out to sea and it gets smaller, that reflection, that band of reflection, gets bigger relative to the boat. So you can see right now, you can see that band of reflection where it's making those circles, right? And as it goes further, you'll just see that that band gets bigger and that reflection gets bigger. Now you can see the contents of the boat being reflected now. Eventually, should I play the whole lot? I don't know. Should I play? Let it go for a minute?
Yeah.
All right. All right. So you can see now that you can see the inside of the boat now being reflected. Eventually, all you'll see is the pilot, and you'll see a double image of that pilot. So it's just like a mast. When they say the mast goes down last as the boat goes over the horizon. Well, yeah, it is. But what you're seeing is like the mast and its reflection. Right? The rest of the boat is being hidden by that band of reflection because of the humidity of the water. So you can see now that it's pretty much most of the boat's gone. All that can be seen now is a top of the boat and the pilot standing on top. And before it disappears, literally you'll just see the pilot. But so this is how it works. And you can see that the bottom of that reflection, that isn't the horizon. The waves are too big, and some of the water is like floating above the waterline there. So yeah. Anyway, so moving on. Again, we've got lots of experiments. I'm not going to talk too much about this, but there's a place where we found like 3 oil rigs. And well, I've only got 2 of them here, but one 6 miles away, one 9 miles away. We put the camera right close to the water, about a foot above the water, and where the horizon should have been at 1.2 miles. But yet we can see both oil rigs and the horizon line behind the furthest oil rig. Again, it shows that it's not refraction. Refraction can't do that. There's no mechanism at all that can bring objects beyond the horizon, right? Symmetrically, so that it looks like it's on a flat Earth. Again, one of the things that people say again about this curvature is that when you see something like this, where this is across Lake Michigan, and again, you're not supposed to be able to see any of that city, but you can see the top of that city. The bottom of the buildings seem to be cut off. So people look at that and say, "Oh, it's got to be a curved Earth." Okay, but yeah, this is the way we see. We see in a kind of pyramid shape. Yeah. So when we look at say a room, say a long corridor, perhaps, the walls start to merge inwards to the center, and the floor and the ceiling sort of merge into the center as well. And there's a point we call the vanishing point, where we literally can't see anything beyond that point. We have a limit to our eyesight. It's an angular resolution of 0.02 degrees. So anything that we're looking at that's going away from us, if the angle between the ground, our eye, and the top of that object is less than 0.02 of a degree, we can't see it. Yeah. So I took this picture again on the Bonneville Salt Flats, and my friend is about a mile away. I can't see. Yeah, so she's about a mile away from me. Now these structures, this is like salt in the foreground. They're about an inch. The sort of little lumps about an inch tall. As you can see, and as it goes into the middle ground, right, that those details start to fade. They get smaller and smaller. So when you get to sort of the beginning of the background here, you can't see those structures at all. That means that those little structures have hit that 0.02 limit. Okay, so you can't really see my friend here in any detail, but you would see that the bottom of her feet would have disappeared because her toes are about just under an inch, so her toes would not be able to be viewed at that point. And I can actually show you how that works. So camera's on the floor, and this guy's going to walk away. Now, as he's walking away, he's starting to see that the bottom of his feet are disappearing. Well, now his ankles have gone. So now we're coming up to his knees. Okay, and in a minute, he's going to get to the end, and he's actually going to disappear beyond the curve of the football pitch. Right, so now his whole waist is gone, and now he's going to dip down. Completely disappear. Okay. Now I've heard people. Let's stop this now. I've heard people say, "Oh yeah, they curve football pitches to drain it. They curve them sideways. They don't curve them long ways. Yeah, that would affect the game. But you can do this on a long warehouse floor, and you get exactly the same results. Yeah." It's got nothing to do with curvature. It literally is angular resolution, and this is how it works. Yeah, and this also speaks to this idea that it must be a curved Earth, because if you see something disappear over the curvature, if you stand up or get higher, it comes back into view. Well, that works on a flat Earth too, and it comes down to angular resolution. So, an object here, when you're sitting down 24 degrees, as soon as it goes further away, that angle gets smaller and smaller until it hits the 0.02. But again, if you stand up, that angle opens up. So now it comes within your limit, within the 0.02 degree limit. So no mystery, quite simple. Another thing people say, if the Earth is flat, I should be able to see Mount Everest from here. Yeah. Does it sound reasonable? Well, I don't think so, because the air isn't perfectly transparent, and we see that it's, especially with in the morning where there's mist and stuff, you can see that the things in the foreground are nice and sharp, and the the contrast is very high. But as you go further, the air starts to have an effect, and everything gets washed out. And you don't know what is between. If you're looking, maybe 1,000 miles away, trying to look at something 1,000 miles away, you don't know what is between you and that. Could be rain, could be sleet, could be snow, could be mist, fog, whatever. Right? Sometimes you can't even see 100 yards. So no, you're not going to be able to see Mount Everest from anywhere. But here's the thing. If you have a digital camera, right, you can. There's these new cameras have an infrared filter on them, okay, to stop infrared light messing up your pictures, right? If you take that infrared filter out, now your camera registers infrared light, okay, and infrared light cuts through atmospheric effects. So here's a picture of, I think it's Santa Monica across the water. And it's taken with an ordinary camera. But this guy, Jay Tolan Media, he basically then takes the same picture with his infrared camera. And now a mountain, Mount St. Jacinto, 123 miles beyond that city, now comes into view. It cuts through all that atmosphere. Yeah. And again, you're not supposed to be able to see that mountain, if the Earth was curved. I can't remember how much curvature there should be with that, but yeah, you wouldn't be able to see that anyway. Another really interesting one. This photo was taken from a mountain in Wales, Yrwyduffa, I think it's called, and it's taken from the top of that mountain, and the height was taken into consideration. But you can see on the horizon the Alps. You can actually identify all of the mountains of the Alps from this picture. Now, the Alps are 700 miles away from Wales, 700 miles, which means the tops of those mountains should be 50 miles below the horizon. There is no way, any way, that any atmospheric effect can bring something from 50 miles behind the curve into view, right? So again, it's the evidence just keeps stacking up for this. Another question: well, how does the sun set on a flat Earth? Well, again, this is just like the experiment with the guy walking away, right? That's the sun he's moving back. And you can see as the sun moves back, it gets lower and lower in the sky. One of the things that isn't shown here, though, that happens in reality, is there's atmospheric lensing, which makes the sun look bigger as it goes further away because it's going through miles of atmosphere. Right? But you can see now the sun, in this case, is setting on the horizon. Okay, and there it's gone. All right. Again, this is on a totally flat surface, right? We can replicate what we see in the sky. And here we go. The sun looks like it's being cut in half by the horizon, right? But you can whip out your P900 and zoom in. And no, it's not being cut in half by the horizon. It's literally still over the horizon, right? It's just, again, it's just perspective, right? On the same topic, we see on the right here, this is what we see when the sun's setting, right? We can see the light from the sun literally come all the way down to your feet. Again, that can only happen on a flat surface, yeah? On a curved surface, the light would actually be on the other side of the curve and maybe right at the on the zenith of that curve, where it reflects off the top of that curve, but you would never see the light literally coming all the way down to your feet. Also, watch how the sun sets here. Notice that the light goes with the sun. It literally is following the sun. Okay. So as it shrinks, the light follows the sun. Hang on, is this going to shrink? Okay. So yeah, you can see that the light is literally is like a ball around the sun, and it's as the sun goes away, the light goes with it in a ball, as it were. But if we were observing the sunset on a ball Earth, okay, we should see the whole horizon sort of get sort of darker all at once uniformly, because literally the sun is lighting up the whole side of the Earth, right? As it goes away, we should see the whole horizon just get darker and darker slowly all at once. But we see that the light goes with the sun. It's the sun that's moving around us, taking the light with it, not we're not going around the sun. Again, it's one of those train things, but the way the light moves is the external thing that tells us it's one, not the other. This is the other thing that people say: if the Earth is flat, then it should be daytime all the time, because you've got a bright white light source above a flat tabletop, for instance, and so the whole tabletop should be lit up. Well,
now I totally understand why it seems that you should be able to see a big, bright, shining light hovering above a flat Earth from anywhere on that Earth. But in the flat Earth model, the known Earth is approximately 20,000 miles across. The Sun is about 34 miles across and about 3,100 miles high. So to put that in perspective, imagine a table 2 meters wide in a completely dark room, and you're holding a small but very bright light bulb, 3.4 millimeters across, and you were holding it about 31 centimeters above the table. What you'd see is a circular pool of light directly on the table, beneath the light bulb. But on the other side of the table, it would be in darkness. Now, it seems to our mind that if you were on the other side of the table, you would see the light because it's, above the table. But that's not true, because on that part of the table, it's in darkness, meaning that the light isn't physically reaching that part of the tabletop. Now, paint a flat Earth map to scale on the tabletop so that Europe is directly underneath the light bulb and Australia would be in darkness. And even though you could argue that you could put your eye right next to the edge of the tabletop and still see the light, well, let's say the pupil of your eye is about 1 centimetre above the tabletop. At that scale, your viewpoint is 100 miles above the flat Earth. And yes, in that case, you would still see the light. This model actually matches observation. In 2014, an amateur rocketry team in New Mexico launched the Go Fast rocket 73.1 miles into the air. But when a flat Earth researcher called Refi studied the footage, he noticed that the moon was visible. But when he checked on timeanddate.com, he found that the moon was actually above Australia at that time. So it would have been impossible to see it if it was on the other side of a globe, but absolutely visible across the other side of a plane from 73 miles up.
In this case, we got like some actual evidence of what I'm just saying here. That if you're in a completely dark room and you've got a light bulb next to a wall, okay, it will throw a pool of light near on the wall near to that light bulb, but the light will drop off according to the inverse square rule. Right, it'll drop off pretty quickly, and so that area quite a bit away from that light bulb is in complete darkness. So yes, as that light source moves around the flat wall, it will illuminate different parts of the wall, and so where that light is midday, wherever that light is. Okay, so as it travels around, midday moves with it. So surely pilots would know if the Earth is flat. Now, here's the thing: if you're flying a plane at straight and level flight over a curved surface, what's going to happen is you're going to gain altitude. You're going to start flying up into towards space, actually, right? Unless you dip your nose down to keep around that curve, right? But here's the RAF doing these low flying exercises. They're 75 foot up, and they're going at 1250 miles an hour, which means they have to correct for 45 feet every 30 seconds. Okay. Now, if you're having to do that and flying, 45 feet above the ground, right, you're likely to be dead. Right? They're not taking curvature into account because there is no curvature, right? So also planes actually fly at a 3 degrees nose up altitude, right? But they've got to, again, if they're having to correct for 45 miles every hour in this case, because of where the planes fly at different speeds, they're going to have to correct for 45 miles every hour if they're going about 600 miles an hour. Okay. And they've got their nose up 3 degrees. How do they correct for that? They literally have to be diving for most of that trip. So when a plane flies in straight and level flight, it is a balance of all these forces, right? So thrust and drag and lift and weight. And the plane can be trimmed up so that the pilot can take his hands off the controls and the plane will fly straight and level. Okay. So if there's any kind of dipping or any correction has to be made, it's not only one thing that changes. As I said, it's a balance. If the airspeed or if the attitude indicator, so if he starts to dip the nose down, right, then the airspeed will go up. The altimeter will start going down, right? And the vertical airspeed indicator will start going up as well, or going down. So if they make any changes, it's not one thing that changes. It's like at least 4 things change all at once. So it's a complex dance, right? When it's flying straight and level, all of those are balanced and all stay the same. Okay. So no, there is no compensating for a curved Earth. I'm gonna sort of skip past that, and so they've also got this in a plane. They've got let me go back here a second. So this is the altitude indicator, the artificial horizon. Okay, it's a gyroscope. Literally, the behind that gauge is a gyroscope that's spun up before the plane takes off, so it can get a reference to the ground. Okay, but here's the thing: if it's spun up at the beginning here before before the plane takes off, right, a gyroscope will stay in its orientation. So you can spin up the gyroscope, right, and keep it on a surface, and then tilt the surface, and the gyroscope will stay in its same orientation. Okay, and that's what happens in a plane. The plane spins up its gyroscope, okay, and then it takes off, and if it goes over a curve, the gyroscope will stay upright. Okay, so as it goes over the curve, the artificial horizon should appear to roll backwards as it goes over the curve of the Earth, but it doesn't. And I ask pilots every time I fly. I sort of give them gotcha questions. Actually, I ask them if they ever have to adjust the artificial horizon in mid-flight, and they say no, we don't. And then I explain this to them, and then they go, "Oh yeah, but we have to adjust the artificial horizon." But you just said you didn't. So yeah, I end up catching them out every time. So I'm gonna go past there very quickly. They also have to calculate this thing called top of descent. So because planes have to have, for safety, a 3-degree glide slope. When they come down to land, they have to be at 3 degrees. So it's a nice gentle slope. So they literally have to use a bit of trigonometry, right, to work out how far away from the airport they have to start their descent. Okay, because it's a triangle. Yeah, so the angle is 3 degrees. They know how high they are. They have to calculate how far away they have to start their descent. Okay, so that's all very well, but if they're on a curved Earth, right, at 37,000 feet, it's 133 miles, but it'll end up nearly 2 miles above the runway if it was a curved Earth, right? Which isn't what happens. Right? So again, I'm throwing all this at you because again, we've got this model that is identical on both sides, and I'm showing you external things that show it's one, not the other. Okay. And again, pilots, as I say, they do know it's a flat Earth because more and more of them are actually admitting it when we ask them.
Can I talk to the pilot, please?
Right here.
You're the pilot?
Hi.
How long have you been flying for?
Like for Delta, 21 years, but maybe like 30 something.
I want to know, because they say the pilots know a lot. Do you think the Earth is flat or no?
I know it's flat.
You know it's flat? How long have you been flying for, you said?
Over 30 years.
And when you tell people that, do they think you're like crazy or no?
Only one person.
Only one person?
Yeah, you're
All
recording me.
So there's lots and lots of videos now of pilots actually coming out and saying, the Earth is flat. They won't do it publicly. There was a woman pilot for KLM who publicly said, yeah, I've been flying for 20 years now, and I know the Earth is flat. And she was immediately grounded. So you come out in public and say what you think, you're out of a job. Okay. So that's why you're not getting people out in the public saying it. They don't mind saying it to us, because TV cameras aren't there. But yeah, they are now coming out in droves and saying, yeah, it's flat. Okay, so I'll move on to motion. All right. So the thing about this heliocentric versus geocentric, they're exactly the same model. They look exactly the same. If you look at the one on the left, which is the heliocentric, which is what we're told is happening, well, it looks identical to the geocentric. It's just where your focus is. Yeah, in the geocentric, you're focusing on the Earth, but it's exactly the same as the geocentric, heliocentric. All right. Again, it's that train situation. Yeah, that's what I said. George Ellis, the cosmologist, basically said that they're identical. You cannot sort of prove it either way based on observations. So they say that motion of the stars proves that the Earth is rotating. Yeah. So if you put a time-lapse camera at the North Star, Polaris, you'll see that all the stars, all of them, turn around the Polaris in perfect circles. That's because they say the Earth is rotating at 1,000 miles an hour around the axis of Polaris. But the Earth is also orbiting the Sun 67,000 times faster than that. Okay, and the Sun is also moving 600,000 times in a different direction, right? Dragging the Earth and all the planets with it, at 600,000 miles an hour. Okay, so how do we get this? How do we get the stars making these perfect circles if that's only 1,000 miles of an hour of motion, and the Earth is moving at 67,000 miles and being dragged by the Sun at 480,000 miles, and so on and so on, right? that there's no explanation for that. So again, the Earth's tilt is pointing at Polaris, right? But if it moves, if the Earth moves any small change, right, it won't be pointing at Polaris anymore. Okay, we're moving around a sun which is dragging us along, and the sun is actually going in a corkscrew pattern as well, dragging us along with it. But yet, with all that motion, our pole, supposed pole, always lines up with Polaris. Okay, in fact, the Georgia Guidestones in America had it used to have a hole drilled through it, so that on a certain night of the year, you could look through that hole, and Polaris would always be centered in on that hole. I think, sorry, any night of the year, actually any night of the year, you could look through that hole, and Polaris would be perfectly centered. Right? It never changes. Okay, there's no explanation why that is. Also, look at the constellations. Well, this is again one of the most famous constellations, the Big Dipper. Now, all the stars, yeah, they make that pattern of Big Dipper, but that's only from Earth, because all these stars are actually different distances away, and they're moving in different directions. Some of them, the ones coloured in red, are moving away from us, right? The ones in green are moving towards us. Okay. So even if we were stationary looking up at these stars, eventually these stars are going to start moving apart or changing shape. Okay. But we're moving as well relative to these stars. So how are we seeing these constellations that stay the same over thousands and thousands of years? As we move, I don't know if you can see it, it's tiny, you can see the stars are moving as we move. It's called stellar parallax. We should see stellar parallax. As we move, the stars should move relative to us. Okay, and I think I've got, so here are the constellations. And this is just simulating our yearly movement around the sun. But as the sun moves as well, I think we're going to get there. As the sun moves as well, we should see that the actual constellation should move out of place, because the stars are all different distances away from us. Yeah, there's no reason in this model why we should see the same constellations, you know, for thousands and thousands of years. This is something else some people say to us. Of course, you don't feel the rotation of the Earth. It only does one revolution per day. Well, that does sound like it's you know, it's not moving very fast. You know, 24,901 miles, you know, per 24 hours. That doesn't sound very fast at all. So think of it this way: if you're on one of these roundabouts, okay, and you know, roundabouts are 8 foot across, and it's moving round once every 24 hours, it will be moving at 3/16 of an inch every minute. So you wouldn't even notice it moving. Now, you'd have to look really carefully to see it moving. Okay. Let's then imagine that roundabout was 1 mile wide. Okay. Now, on the edge of that roundabout, it's now moving at 690 feet an hour, which is 2.2 inches a second. You'll see it moving very slowly. Okay. But now let's imagine that this roundabout is, if it's 283 miles wide, it would be 37 miles an hour, which is 54 feet a second. Right? You'd be flung off at that speed. Right? I put that speed in there because that's exactly the speed that the gravitron goes around. Has everybody been on a gravitron at the fairground? No? Okay. All right. Well,
round, is it?
Yeah, it goes round and round. You're on the inside, and as it goes round, you're stuck to the outside, and you can actually like clamber up and go upside down or whatever, because you're pinned to the wall. Okay. That's only 37 miles an hour, right? And if you were on the outside of that, of course, you'd be flung off. Okay. So if that roundabout was 8,000 miles wide, now it's moving at 1,037 miles an hour and, 1,500 feet per second. You'd absolutely be flung off that earth. Yeah. And you can see, but at any time, if you could manage to hang on to it, you could run into the center. And once you get like 4 feet from the middle, you're still only going at 3/16 of an inch every hour. Yeah. So yes, it's a fallacy. They're appealing to your ignorance of how speed works. Yeah. So yes. Also, this is what happens if you've got like a foam ball that's soaked in water. As it spins, the water starts to collect at the equator. Okay, so you can see the water shooting off as it spins at the equator of the spin. So why is there any land at the equator? Because as the earth spins, the water, which readily moves, should actually collect at the poles. It's not collect at the poles, collect at the equator. So there shouldn't be any land at the equator. And you can't say that, oh, the equator's higher up than most of the places on Earth. No, actually, the Danakil Desert, for instance, in Africa, is one of the lowest points on Earth. Yet it's totally dry. So why, if the Earth is spinning, is there land at the equator? Again, I've asked this question to Neil deGrasse Tyson, and he refuses to answer me. Another thing people say is that, well, when you're moving at a constant speed, you won't feel the motion, right? Just like if you're on a train and the train's going at 40 miles an hour, 50 miles an hour, right? You don't notice any actual motion. If it was nice and smooth and there's no bumps, you wouldn't know you were moving. Yeah, that's absolutely true. Yeah, it doesn't matter what speed you're going at. You're going in a straight line at a constant speed, you will not notice the motion. However, if you go in a circle, that's acceleration in different directions. Okay, just like if you're going in a car at a constant speed, right? You would not feel anything. If you're going straight line in a car at constant speed, you won't feel anything. You could juggle in the back, yeah, and you wouldn't notice anything. But as soon as that car goes round a bend, right, you get thrown to one side, and there's no way you're juggling, yeah, because motion in a circle is acceleration, and we feel acceleration. We feel acceleration, the slightest bit of acceleration. So motion in a circle is acceleration, and we would feel it. Here's an example. So it's going in a straight line, constant velocity. Do you think they felt that? Yeah. As soon as they went away from that straight line, yeah, they were thrown to one side, because motion in a curve is acceleration in different directions. Yeah. Another proof, apparently, that we're moving. This is from the 1800s. Was a guy called Leon Foucault. Foucault's pendulum. He actually did an experiment with a gyroscope, where he surmised that if you set a gyroscope spinning, again, it will stay in its orientation. But as the Earth moved, it should move as well. It should stay the same. And from our perspective, it would look like the gyroscope is moving by itself. It should move 15 degrees every hour or so. Yeah. And he did this experiment with a hand powered gyroscope. So it was like a string that he pulled and spun up the gyroscope. And he claim to detect the Earth's rotation, but we've done the same experiment.
Let's start the clock.
But with a precision gyroscope, right? Precision gyroscope in a plane with a plane's at it was it I can't remember what it's called. It's a direction finder or something. Can't remember, but we've left it to run for 10 minutes or so, and it doesn't move at all. So we can't detect the Earth's motion with a precision gyroscope, yet somehow Leon Foucault managed to do it with a hand-spun gyroscope. So no, we've done the experiments. We can't detect it. Also, Earth without its water apparently looks like this. Yeah. So it's not a smooth billiard ball, right? And also it's got millions of tons of water, sloshing around on it. So how does it rotate smoothly? Anyone who's ever had to have their tires balanced knows that if the weight on that wheel is unbalanced in any way, that wheel's going to be shaking as it hits a speed. Yeah. Why is this somehow managing to spin, nice and smoothly? Yeah. There's no explanation for that. Okay. Very quickly, there's lots of experiments that have shown that the Earth is stationary, but nobody in the scientific community is actually told about them. These experiments have just been squashed. Okay. In fact, the cosmic microwave background radiation proves that not only is the Earth not moving, but it proves that Earth is the center of everything. Okay, they did this experiment 4 times and got the same result every time, but they don't talk about it. It's not mentioned. In fact, there's a documentary called The Principle that you can find, and it's somebody who basically got all these scientists and got them to admit to this, but they didn't realize they were on a documentary talking about the Earth being the center of the universe and all that. But there you go.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature. Or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Yeah, this is my favorite physicist, Richard Feynman, and he does a whole lecture, and he basically says, you can have all these amazing theories all you like, but if it disagrees with experiment or your experience, then it's wrong. Doesn't matter who came up with a theory. If it doesn't match what you can see and experiment with, it's wrong. Okay. And what I've shown you, everything disagrees with the theories that we've been presented with. So final section, space, the fictional frontier. Okay. So there's no sound to this. I can't find the sound. I think they took it off deliberately, but this is the first manned space, first manned venture into space. It was a balloon, a helium balloon with this capsule attached to it. I think it was 1948. And they went up, and I can't remember how far they went up, but they went up and they sent back a picture of space. and we'll see what that looks like. Now, remember, 1948, nobody had ever seen space before. Okay, they got no idea what it looks like, and this is the very first images shown. And I'm going to have to try and stop it at the right moment. So that's them going up. And this is space. Let me go back a second. I want you to see, look at the moon. I'll try and stop it. Look at the moon. You see the crescent moon and the star in the middle of it there. Okay, literally, this is what they palmed off to people as space back in 1948, because again, nobody had seen it before. Right.
So, like, a simple question would be, can you see stars in space? So, NASA, can you see stars in space?
Says you can see the stars.
Oh yeah.
You know, and pretty much all the time you can see the stars.
Yeah. It's not a black void. I mean, it's black, but there's all kinds of little polka dots.
There's all the stars there, and the cool thing is about it, you can see it during the day.
Yeah, you can, and there's more than stars. You can see planets. You can see moons.
You see the gas Magellan clouds of the Milky Way galaxy.
Okay, so you can see stars from space.
And when you're in space and you're looking into deep space and you're on the sun side of the orbit, the sunlight washes out all the starlight, so you can't see any stars, just like here on Earth. But then when you look out into deep space away from the sun, it's the darkest black you can imagine, right? And so what happens is you really lose your depth perception. You can't tell if something's close by or far away.
Okay, so you can't see stars from space.
You see lots of points. And you see lots of points, and that literally millions of them. You know, there's, you know, the thing about Carl Sagan, billions of billions of stars. There really are billions and billions of stars, and you can see them. In fact, they're so numerous, it's very difficult to pick out the constellations you and I see here on the ground.
Okay, so you can see stars from space.
The sky is a deep black when viewed from the moon, as it is when viewed from cislunar space, the space between the Earth and the moon. The Earth is the only visible object other than the sun that can be seen, although there have been some reports of seeing planets. I myself did not see planets from the surface, but I suspect they might be visible.
Okay, listen, so you cannot see stars from space. That's the final answer.
And we have to realize that in space, without the intervening atmosphere, the heavens are 10 times as bright, stars 10 times as numerous, because there's no atmosphere to block the light.
Look, I'm going to ask this question one more time. Can you or can you not see stars in space?
We were never able to see stars from the lunar surface or on the daylight side of the moon by eye without looking through the optics. I don't recall during the period of time that we were photographing the solar corona what stars we could see.
I don't remember seeing any.
They can't even remember seeing stars. They can't remember if they saw stars when they went to space. Yo, I went to Disney World when I was 6, and I remember what my favorite ride was. They went to space and don't remember if they saw stars in the sky. So, yeah, I'm crazy because I don't believe what NASA is saying.
Now, interestingly, let's see if I can find it. Interestingly, when Michael Collins over there said, I don't remember seeing any stars, right? You see Neil Armstrong, get really uncomfortable because Michael Collins was the one who stayed in the command module. He went round the dark side of the moon, right? So on the dark side of the moon, which was shielded from the sun, he should have had the most spectacular view of stars, right? Because there's no sunlight or anything blocking his way, right? But he says he doesn't remember seeing any stars whatsoever. That was a big, big mistake. Also, here we go. Somebody else who says, I've seen the space shuttle launch into space, you idiot. Yeah. Well, this is a shot of a space shuttle launch from an aircraft. Okay. And can you see it? It's in the little bright lights in the center there. Now this is interesting because right here is where the space shuttle crosses the horizon, which means at that point, since we know that the plane is 35,000 feet, we know that that shuttle was 7 miles high. Okay, so I actually extrapolated from that image. So we now know it's 7 miles high when it crosses the horizon. So I extrapolated the height, and then I actually just followed the path of that shuttle. Okay, and I noticed that it actually always curves under 70 miles. Curves under 70 miles. And every launch flies under that 70-mile limit. Okay. Now, I've already played this, actually. I've already played this. This was that Go Fast rocket, right? And I'm going to advance it. Now, if you remember from earlier, it was going up and it was spinning wildly as it was going up really quickly. So I'm going to start it from near the end. Right, so it's near up its maximum height, which is about 73 miles up. Watch what happens. So remember, it's spinning wildly and it's going up really quickly. And all of a sudden, it hits something and stops rotating, stops going any higher, and just starts moving down or falling down. Yeah. There seems to be a barrier at about 75 miles up, right? Which means, let's go back a second, which means all of these space shots, right, all curve under that 75 mile limit, okay? Because they know they can't go any higher. Which leads also to this idea, okay? If, as they say, there is no solid barrier between us and space, well, how can this be? How can you have an area which is pressurized next to a vacuum? Yeah, we know that if you have a pressurized container and you open it next to a vacuum, right, the air pressure will equalize into the vacuum, right? They say that it's gravity holding the air to the earth, but at the top of the pressure there, the vacuum will be acting on it with the maximum strength. It should start pulling the topmost molecules of air out into space. And now there's a new topmost layer, which will then be pulled out into space and so on until there's no more air left. This is how strong the vacuum is. And that is just a relatively weak vacuum up against, normal air pressure. Okay. It's a massive amount of power. Okay. NASA has a vacuum chamber, right, which simulates 10 to the minus 6 torr, which is the measurement of vacuum. But no, it's got 8 foot of concrete and think about 2 foot of steel to manage to contain a vacuum of 10 to the minus 6 torr. Now, space is 10 to the minus 17 torr, I think it is. So orders of magnitude much more powerful than 10 feet of concrete and 2 feet of steel can handle. Okay, yet somehow this spacesuit was able to protect a man from that level of vacuum. Yeah, it's cloth and rubber spacesuit, right? So this is the only guy who's ever actually tested a spacesuit in a vacuum. Okay.
They all do. And Jim was at a vacuum in the spacesuit. With all the air sucked out, all that protected him was his pressurized suit. Then something happened. I heard over the headset that he was losing suit pressure. The tube pressurizing his suit had become disconnected. He was in serious danger. It wasn't any feeling. It was just happening so fast, trying to get the chamber back to a safe pressure and Jim to a safe pressure inside the suit. As I stumbled backwards, I could feel the saliva on my tongue starting to bubble just before I went unconscious. That's kind of the last thing I remember.
So the only time a spacesuit has been tested, right? The guy almost died because, and it wasn't a hose pipe got disconnected, right? Literally, they were testing the suit and it nearly killed him, right? They never tested a spacesuit after that ever again. Which, if it failed, then they would have tested it because they were going to send people up in space, weren't they? Yeah, but they never tested the spacesuit ever again.
They all do.
So I noticed this this little codpiece thing on Neil Armstrong's spacesuit. Yeah, I was thinking, what's that? So it's like, attached by a few poppers there, right? So I did a bit of searching for more images of his spacesuit, and guess what I found? Under that codpiece is a zip, so that they could go to the toilet. So this is a joke, the suit was there just to fool us, right? That there's no way a zip can protect from the vacuum of space. Yeah, it's just absolutely ridiculous. And that codpiece was there to hide it so you wouldn't know. Because these actonauts, yeah, while they're in that suit, they'd have to go to the toilet somehow, yeah. So very quickly, look at satellites as well. So this is a kind of average size of a satellite. You can see with the guy there next to it how big it is. But it's essentially the size of a jet engine on an aircraft. And this is a jet engine. This is an aircraft from 35,000 feet. Now I'm zoomed into it, so that's me zooming into it. And the size of that jet there is the actual engine on that jet is it's a pinprick really, but that's only at 7 miles up. Okay, they're trying to tell you that these are satellites moving across the sky, the night sky, and yet these satellites are anywhere from 200 odd miles up to 12 or 1400 miles away. Yeah. And yet it's the size of a jet engine on a 747. Yeah, there's no way you should be able to see it. So the other thing is notice again. I'll just go back. Notice that you see it's lit up continuously. See, it's not sparkling or anything. It's just a light that's moving slowly across the sky. But the satellite itself isn't a smooth ball. It's got jagged edges. It's got bits where the light will catch. Just like the mirror ball there, it should catch the light every now and again as it's moving along the sky, and it should be flashing and going dark and what have you, just like the mirror ball there. But how does an irregularly shaped object catch and reflect the light constantly like that? Yeah. The other thing is that on this image here, the sun is on this side of the earth, okay? And so it's lighting up that half of the earth. This half is in darkness because it's nighttime. And here it's like midnight, okay? So over here is midday, over here is midnight, okay? Now you can lie in a field at midnight and look up at the sky, and you can see these lights moving slowly across the sky, and we're told that they are satellites. But here's the thing. They are literally in the Earth's shadow. Where are they getting the light? Right? Because the whole Earth is literally in shadow there. yet you can look up and see, supposedly the reflected light from the sun bouncing back down on you. There's no way, and these are through Earth orbits, low Earth orbit here where the ISS is, and then the limit, which is 1,200 miles, right? So anything in here in this shadow, you wouldn't be able to see because satellites don't have lights on them, right? So how are you seeing these things? There's supposedly something like 50,000 satellites up in space, yeah. But at no time do you see satellites move across the face of the moon. Okay, you should see little points of light just whizzing across the moon, because the moon is in between the satellites and us. We don't see it, yeah. So I'm just going to show you a satellite deployment, right, and see if you can spot something.
Of life in orbit. Our first task, of course, was to deploy Telsat. It was a nighttime deploy, and so this is a TV picture, nighttime TV picture of the deploy. It looks more or less like in the day, you just can't see it too well.
Did you catch that? Well, I'll slow it down in a sec. Hang on.
That is just a quick scenes of life in orbit. Our first task, of course, was to deploy Telsat. It was a nighttime deploy, and so this is a TV picture, nighttime TV picture of the deploy. It looks.
Can you see that? It's a wire.
Oh.
The thing's going up on a wire.
Looks more or less like in the day, you just can't see it too well.
Okay, and they cut away from it very quickly. Yeah, so it's all theater. It's it's wires and models and everything. Yeah, it's a joke. It turns out that NASA is the world's biggest consumer of helium in the world, and they're literally launching satellites on balloons from Antarctica. So they launch these balloons from Antarctica. These balloons go up into the jet stream, and they literally follow the jet stream around the Earth. Okay, and sometimes they crash, and when they crash, they're still attached to the balloons. So this is one that crashed in Africa, and you can still see the balloon that it's attached to. Yeah. So they show you this orbital pattern, right? This weird kind of looping pattern that not only the ISS but all the satellites seem to go around. Okay, but this is an artifact of this type of map, this flat map, right? If you trace the path of these satellites, right, on the map, you get this strange kind of sine wave. But on a flat, and there you go, on a globe, that's actually where the jet stream goes. That's how the jet stream looks, or the northern jet stream. There's also a southern one, but that southern or northern jet stream literally does that looping pattern. So that's what I'm saying. They launch these balloons into the jet stream, and they follow the jet stream. But when you look at the jet stream on a flat map, circles, right? So as I said, that looping pattern is when you try and take that flat map and then wrap it around a ball. That's when you get that looping pattern. But on a flat Earth, it's literally circles. So they put these satelloons into the jet stream, and they just start going round and round the Earth like that. And same with the ones in the northern hemisphere. Okay. So it's a very quick look at the International Space Station. So the so-called film, the space station, transiting the moon. Every now and again they'll say, "Look at the moon. You'll see the ISS go past it." But the ISS is the same size as a jumbo jet. Okay. And it's supposedly at 253 miles away from the Earth. Yet a jumbo jet flies past the moon, and it's around about the same size. Yeah, even though the jumbo jet is about 7 miles high. Yeah, no, something stinks, doesn't it? I'm gonna skip this. This is going for. Oh no, I might as well say this. Yeah, so the ISS is supposedly orbiting the Earth. Okay, and this idea of orbits is essentially this object is going so fast, and it's trying to fall to the Earth, but as it's going so fast, the Earth is curving away from it, so it keeps missing the Earth as it's falling. That's the idea. Okay, so it's like there is gravity still, but literally the speed it's going is keeping it in orbit. And it's kind of like, if you've got like a pail of water on a string and you're spinning it very fast, yeah, the water is going to stay in the bucket, right? But here's the thing: if that was happening, like the ISS was spinning around the Earth like that, the astronauts would be a red stain on the side of the spacecraft. They'd either that or they'd be pinned to the side of the spacecraft. Centrifugal force. Yeah, they're just ignoring that. Right? But there you go. Also, we've got an analog of the ISS on Earth in a submarine. A submarine is in a harsh environment, okay, which where there's no air, okay, and yet all the serviceable parts of that submarine, every part that might need to be fixed, is on the inside of the submarine. So, but unfortunately, when they created the ISS, they put all the stuff that needs to be fixed on the outside, which doesn't make any sense whatsoever. Yeah, because they have to keep doing these spacewalks to fix things outside. Yeah, how does that work? Nobody can explain that to me with any sense. And how would you design a spacecraft like this? It's just like, no, you're in the most hostile environment ever, right? Where you can't make any mistakes, and you're in an environment like this. No, it doesn't make sense whatsoever.
I think that as well, when you go to the Natural History Museum and they show you this same display that's been like there since the 60s or wherever, of that one space shuttle, which is so tiny it looks like a tent. And it's all broken and it's got bits of foil around. And I think that's supposed to have gone to the moon. Like, it's like a toy.
Yeah, it is. It's really the lunar lander looks like it's something a bunch of kids put together with old scraps,
Yeah, exactly. And the thing is, people fall for it, don't they? I mean, I fell for it at one time, but I was looking at it again. Bizarre.
Well, this is the thing. It was meant to fool the people from 1969 who'd never seen anything like this before. Okay. Right. Now we've been able to go back and look at it, and we've got a different sensibility now. We understand a bit more, and we can look and go, wow, that doesn't make sense. That can't work. They say the lunar lander, the walls of it were as thick as thick aluminium foil. So heavy duty, aluminium foil. So you could poke your finger through it. How does that hold in air pressure? All right. So against that 10 to the minus 17 torr, again, no. So if you spend any time looking at the International Space Station, you're going to start seeing errors. You're going to start seeing problems. So this one is actually from looking at the Chinese space station, because they've got into the act as well, right? So every time that we see where they do their tricks with water, okay, water always forms a sphere, okay? Now, you can put it in something, it'll always try and form a sphere, okay? But when we look at the Chinese space station, they end up having a glass of water on the counter, and that glass of water had a flat top, which means it was acting under gravity or this idea. They're not in space because that water in that glass should have formed a sphere and maybe even floated out of there. Yeah. But no, that was one of their mistakes. See if you can spot this mistake. It was very quick, so you might not have seen it. Look again. You see it?
Something drops down.
You see in the background, while they're floating around in the foreground, yeah, water drips off the ceiling. Yeah. They couldn't help that. They couldn't stop that, but it happened in the background. Yeah. This guy as well. So he unscrews something and a screw drops to the floor, even though he's floating to get there. Yeah, he unscrews something and it drops to the floor and he's scrabbling around on the floor looking for it. Yeah. Again, you look at their footage and you just keep seeing the mistakes. Here's another one. Watch. This is them doing CGI.
Yeah.
Very bad CGI.
Yeah.
And again, the more you look, the more you'll find. The more you'll find. And this is another one where they switched off the video layer too quickly. And now,
thank you very much again. Thank you for your time. Have a good flight and many more exciting experiments on the orbit.
Now let's switch off the foreground layer. Watch this. Notice the stuff in the background isn't changing.
Station, this is Houston ACR. That concludes the event.
And they switch away from it very quickly. So those things that started to smear were on a foreground layer. So and when the broadcast, they thought the broadcast had ended, they switched off that layer and it all started to go funny. But the background layer didn't change. Yeah. And here's them, a few astronauts doing their little hand signal. Yeah. Again, this is all by the same group of Luciferians. So last bit. Why would they want to hide the flat Earth? Why would they do this? Well, if you believe in the ball Earth theory, what comes along with it is the theory of evolution and the Big Bang theory. Yeah, you put all that together, and you get this idea that we are a tiny blob of goo that's crawling around on a speck of dust in this infinite void with trillions and trillions of other specks of dust and maybe billions and billions of other blobs of goo. There's nothing special about us, right? Nothing special about us whatsoever. We're insignificant and unimportant. There is no creator, right? Everything about us came about by accident, right? There is nothing special about you. Okay, that's the message that gives. So we're in an uncaring, accidental, infinite, and purposeless universe. Yeah, and so essentially, if we have been inculcated with that idea, right, powerful people on Earth can tell us what to do, right? Because we're psychologically weakened by this. People with power on this Earth can literally give us a purpose. And what's the purpose they give us? People might disagree with this, but the purpose they've given us is get good grades at school, get a good job, buy lots of meaningless stuff, buy bigger, faster, meaningless stuff, retire and then die. That's it. That's the grand purpose they've given us for our lives. Yeah. But if you know that this is a created place, you will know that there is a creator, right? That there is a purpose to your life, right? That you are important. Yeah. If this is the universe, then every life here is important, is sacred. Right? That will change your perspective on this world. So yeah, they want you to believe that this is a cold, harsh, survival-based dog-eat-dog world, but that's just an illusion. Yeah. If we're in this closed system, that means every drop of water that's ever been here is still here. Every erg of energy that's been expended is still here. It doesn't leave. Right? There's always going to be abundance here. There's never going to be lack. Lack is literally just an illusion. So yeah, the earth is abundant, and this universe was created for you, and it's here designed to sustain you. So shouldn't be any fear about living this world. So that's it. Hope that was useful.
Oh, that was brilliant. Yeah. I before I forget, I want to mention, have you read 1984, Dave?
Yeah.
So in that, they do allude to being stuck in a dome.
They also say that, yeah, the stars aren't millions of miles away. They're just some miles away. Yeah, I couldn't believe it when I had to read it back again to see it.
Yeah. So it's funny because now that, you know, I'm coming into the whole flat earth stuff, because it's true. They say when you get into it, you can't go back. And I'm beginning to sort of see it everywhere, really. Yeah, it's fascinating, isn't it? Yeah.
But that's what happens because, you know, once you start thinking along these lines, you start looking at the world differently. And so you start questioning, you know, things that you've just accepted, you know, you just start looking at, hang on, I wonder if that, and if you go and look into it, you start to find that, and this is what I found. I would ask authority, I would ask the experts, and I would get answers that I knew were wrong. And it's like, well, hang on a minute, that's wrong. And I can go to a book and go and find and look it up and say, yeah, it says here it's wrong, you know, what you told me. So it was like they were trying to dispel what I'm saying, and they're saying anything to try and get rid of what I'm saying. And you know, before I started this journey, I was one of science's biggest fanboys. I'd listen to science lectures, you know, while I worked all the time because I loved it so much. But this made me realize that I've been lied to, and they were continuing to lie to me and trying to gaslight me to believe that I know nothing about anything. But yeah, anyway, as soon as you start asking authority and experts, you find that they're not going to tell you the truth.
And you're entitled to, anyway, compile things together and believe whatever you want without needing to be criticized for it. I mean, you know, we're all entitled to be able to have our own view, but it's really weird how that is really pushed down, I think, more than even all the alien stuff. Okay, all that alien stuff's out there. It's all phenomenal. It's all become commercial now anyway, right? But the flat earth stuff is like real holy grail. No one's going to go there. It's so bizarre.
One of the slides I took out was the reason why you can't find proper flat earth stuff on social media anymore, because YouTube made a policy, you know, especially for flat earth content, so that if you look for it, you'll find authoritative answers. You'll find the mainstream view that flat earth isn't real.
I don't really need to hear what you're trying to provide. I want to know how you're dealing with all these conspiracy theorists on your platform.
So the first way is by demoting low-quality content and promoting more authoritative content, and the second is by providing more transparency for users. So we're introducing boxes that provide factual information at the top of results that have shown themselves to turn up a lot of information that is counterfactual, such as searching for the earth is flat on YouTube, where you see a lot of...
Your response is to put a box saying, nope, the earth is not flat.
Correct.
Okay.
All right. And even if you knew the name of the video you're looking for, right, you can put in one of my videos, The Biggest Lie of All. You put D Murphy 25, you know, the channel name, and search for it. You won't find my video till about the 10th page. Okay, you'll just get lots of mainstream views saying no, flat Earth doesn't exist. It's there's a reason for it. I think they're setting us up for the alien invasion. That's what's being set up right now. And they have to have people believe it because, as Ronald Reagan said, right, an alien invasion is what will get everybody together to demand a one world government. Right, and that's obviously their goal, and they're setting us up for this fake alien invasion. But if you know that the Earth's flat and there isn't space out there, you're not going to be fooled by it.
Right.
So that's why they need people to believe in the ball Earth.
So it's really interesting because all the have you ever heard of Thorhan? And these Venusian from Venus, the fact that they'd come over and stuff in the 1940s and met with the government and everything. So, it's gone.
Oh, I was just going to say, so part of because I've been researching a lot of other stuff. I'm not just flat Earth.
Yeah.
But I found that these aliens aren't aliens at all. They've always been here. They're demonic, not alien. Okay, and the whole Roswell thing. So Roswell is what kicked off, aliens into the public consciousness. Okay.
Yeah.
But you'll find that who's behind Roswell was a guy called Jack Parsons and L. Ron Hubbard, who were disciples of Aleister Crowley, who was the most wicked man alive. He called himself the Beast 666, and he was opening portals for these demons to come in. And he wrote a book, and in the book he drew one of these demons, and a demon looks exactly like what we would call an alien grey. So Jack Parsons and L. Ron Hubbard took over Aleister Crowley's work when he died, and apparently they opened a portal and they couldn't close it again, and that was just before Roswell. Right, so there's a guy called Jack Valet who was like the top UFO researcher. If you ever saw Close Encounters of the Third Kind, right, the Frenchman in that film was supposed to be Jack Valet. Okay, he's this top UFO researcher, and he concluded that these UFOs aren't physical; they're demonic and spiritual. Right, so that's what's going on. It's an invasion from more of a celestial invasion rather than an alien one, and they've always been here. They keep renaming themselves. They've been called demons, jinn, genies, nature spirits, you name it. Now they could be called aliens.
Yeah, no, I mean, so two things there. One is when I saw the footage of this supposed president of Venus come over, who actually just looked like a human in a suit, I'm thinking, could that be on the other side of the Antarctic wall? I mean, could it be that they've got civilizations there, and so rather than it being outer space, it's just actually on another side of this Earth, behind the wall, perhaps. But also, interesting you've just said about portals, because you're the third reference to portals that I've had all weekend. I don't know if you know about the what happened in Toulouse or in Paris when they had a parade with Black Lilith, and oh my goodness, it was on Thanksgiving's Day. They had a public parade of the Black Lilith and one of those minotaurs, massively created, like it was a public opera sort of thing.
Oh, this is that scorpion, a woman,
Yeah,
and a bull. Yeah, I saw
yeah.
that. Mm.
And apparently incantations and spell work going on there. And they're now, I mean, people saying that Paris is the head of Satan. Basically, it's the headquarters is France. And they're
Actually,
opening up portals.
actually, not far from it is that area because
Mm.
first of all, Paris used to be the prime meridian. Um, Greenwich is now, but it was called the Devil's Line
Oh.
back then. And not far from there is Lyon. Now, I always thought Leon meant lion, yeah, but it actually is short for Apollyon. Okay. Now, near and Lyon and Geneva, that kind of area, yeah, that's where CERN is.
Yeah.
Okay. And right in the middle of CERN is the Temple of Apollyon. Okay. And the Book of Revelations, which I don't have much regard for, to be honest, it basically says that the bottomless pit will be opened where Apollyon will come out of it, the destroyer. Right. Now, CERN is around that area, right, encompasses that area. Outside of CERN is Shiva, the Indian version of the destroyer, coming through a portal. Yeah.
Yeah.
And the guys at CERN have said now that they've found the Higgs boson, yeah, now they're trying to open a portal to a different universe, as they keep saying that.
Yeah. It's like, you know, the Gothard Tunnel as well.
I saw that.
Yeah, I mean, that was bizarre. Um, it's yeah. Do you know Thoth, the book of Thoth?
Yes.
So they talk about portals. He talks about portals in there.
Well, talk about more than that.
Mm.
If you've looked at Tablet 8, it tells of, and I think this was an event that happened before, it tells of these reptilian people who have technology that make them look like humans. And they crept themselves into positions of power.
Darkness,
right?
yeah.
Yeah.
Hidden
And
in
it
darkness.
says there was a very enigmatic line in it. It said, only by sound can their faces be seen.
Mm.
Right. So there's this particular sound that reveals their true appearance. And it goes on to say that one of the masters of this time found a word that would, reveal their faces essentially, and it said something like serpent-headed when the glamour is lifted.
Yeah.
Right. Now, interestingly, as I was reading this over again, I came across this idea about all the bells being removed from the earth. So over the last century, they've literally removed bells. There used to be huge bells, literally there were bells in every town, right? And I realized that, okay, if these creatures, and the tablet basically says these creatures were defeated, but they're going to come back, right? So if they're going to come back, wouldn't it be prudent for humanity to have some way of detecting them? It turns out, I think, that these bells emit a frequency that reveal the faces of these things. So that's why slowly they got rid of these bells from everywhere, right? And so that they couldn't be revealed. And now they're taking over. We're right back there again, where these creatures have taken over the positions of power in this world. I know it sounds really conspiracy theory and everything.
No, don't worry. That's all. I mean, that's where I am anyway. And also, with the music, they've changed that the
frequencies.
What is it? The official line for music that, so none of that we're not hearing correctly, and it's just the whole frequency's down, isn't it? It's not where it should be.
This world is very, very different to the way people perceive it. We're living in Disneyland. Yeah, the
totally.
people in control have constructed this place that looks a certain way on the surface, but you go below the surface, you see it's very, very different.
They show you that in the opening ceremony of the Gothard Tunnel. There's a bit where they bring in a circus, literally, and it's like they're just falling man. And there's actually a pope run in that ceremony with 666 on his hat. It's just, I mean, it's all in front of your eyes, isn't it? When you know it, and you just realize how blatant it is now.
Yeah,
it's crazy stuff.
I think it's the most exciting video game that anybody could play. Yeah. I was just listening to somebody who was saying that, why is the world so horrible? Why is the world, why is it so difficult to live in this world? Well, nobody wants to play a game there's no fun to it. I mean, the game of snakes and ladders isn't fun without the snakes. If you play snakes and ladders and you take one move and you're right to the end, there's no fun. Yeah, there has to be challenge, there has to be adversity. Yeah. And we're not really these bodies. This is just the avatar that we're using to play the game. Yeah. So we think we're these bodies, so we're taking it too seriously. Yeah. This is an amazing game. Doesn't matter how dark it gets, it's still an amazing game.
And when you know you're eternal, it makes it better.
Well, that's the problem we have in this world. There are people or beings here who aren't eternal. They're not going to make it past this, and they know it. So they're inflicting their pain on us essentially.
I'm sorry to interrupt, but may I ask? So I've just been thinking.
Sorry.
Okay then.
Sorry, go on.
Yes. So if there is no space, so do we not have other planets as well, like Mercury, Venus, Jupiter, Pluto?
Nope. Just think of those names that you're reciting. Yeah, they're the names of gods. The gods are actually the fallen angels, right? And angels in the Old Testament are connected to stars. They're stars, right? And there were a certain class of star of angel called the watcher angels. So they stayed close to us to watch over us. Yeah. So they are the stars that wander in a different pattern to all the other stars that all move around together. Yeah. So there was seven, I can't remember, it was seven. There were a certain number of stars that would move differently to all the others, and they were closer to us. Right? And they're not planets, they're not rocky places that you can go to. They're lights in the sky. And we can simulate that with something called sonoluminescence. Have you heard of it?
I have, I think.
Right. So if you get like a glass container, right, full of water, and you pass ultrasound into it at a certain frequency, all of a sudden it creates bubbles that get created and then destroyed very, very fast. So fast that it generates a massive amount of heat and light. So you end up with what they call a star in a jar. And it looks exactly like a star sitting in the middle of this water. All right, sonoluminescence it's called. So yeah, these planets and stars, they're just lights in the sky.
So how do you view, what's your opinion of astrology then?
Astrology, well, again, that's the study of the movements of these heavenly bodies. My view is that I want nothing to do with it, because the book of Enoch basically tells us that we're not supposed to do that. We're not supposed to divine by the stars. so I don't do it. So I don't have any. I don't talk about it at all.
Okay, thank you.
Okay.
Thank you so much, Dave. Yeah, I thought that was a brilliant presentation. I really enjoyed it. It really, you've just given me more and more and more evidence as to why I think the Earth is flat. Really, more and more. Yeah, all this stuff makes sense because I guess when we, growing up thinking it's a globe, you take it for granted that all the facts are correct because nobody really goes to check all these facts. But when you've sort of proven them the other way around. Also, I do remember growing up, or sometimes when you look at very old maps, the world is flat. And I remember seeing like other places, existing on a map on a flat Earth. I don't know, it's just a memory that I do have. So I always sort of wondered, and then you've got Gulliver's Travels and all that business, like there are other places going on. It's just bizarre.
Well, the map that we're all used to is actually called the Mercator projection. Okay. So the shapes of the continents that we're all, familiar with, they literally come from this one particular map called the Mercator projection. The actual shapes and sizes of the continents are very different from that map. Right? That map is just a navigational aid for going east and west, for sailors. The like Africa is way bigger than it's shown on that map, and it's longer as well. And you can literally fit Europe, America, China, and probably more into Africa. Okay. But all the depictions of the Earth show the Mercator map. They don't show what the Earth looks like. And we've got no idea what's actually on the Earth because, we've not been able to travel there. And we're only trusting what the system is telling us is there. So there could be whole other continents and we wouldn't know about it. Yeah. They patrol the sea. You're not allowed to go to Antarctica because they patrol the sea. And there were 2 people actually just recently. There's a video you can go and watch on YouTube with a bunch of Australian fishermen. They're in this boat and they say, let's go out to the ice shelf. And so they head off to the ice shelf and all of a sudden a warship appears and tells them to turn back. Right?
Yeah, I find that bizarre. Why on earth can't we go to Antarctica? I do find that really weird. Like, as a free citizen of the Earth, why can't I travel to Antarctica? Like, why, It's
because
just
the answers are there. One way or the other, the answers are there.
Bizarre.
Yeah.
Dave, thank you so much. Thanks for your time. I really appreciate it. I will send you a copy of this Zoom link.
Okay.
And you can use it any way you want.